This is Group 1A's lab video for the Gaussian Beam Profiling Lab by Olive Mayer, Eliana Stilson, and Brendan Bamberg. This lab deals with profiling a Gaussian beam by determining important characteristics, such as the laser's Rayleigh range, beam waist, and beam divergence. Let's start with a quick review of these beam characteristics that we'll be encountering in this lab. The beam waist is the smallest radius of the beam along the optical axis. At this point, the wavefronts are planar, meaning that there is no divergence of the laser. As for the Rayleigh range, this is the distance from the beam waist in which the laser is still considered to be collimated. The following techniques will be used in order to actually determine what these characteristics are. To ensure accuracy in our measurements, we align the Heaney laser parallel to the table using the same method from Lab 1. Similarly, we also aligned our microscope using an objective with a small magnifying power. We then set up a knife edge on a translation stage so that it can be adjusted orthogonal to the optical axis, and then placed a photodetector behind the knife edge. Starting with the knife edge completely covering the laser from hitting the photodetector, we adjusted its translation in 10 micron increments and collected power data at each one. This process was completed 2 times, both close and far from the laser. After normalizing our data, we compared it with a theoretical beam profiling curve given by the function on this slide. Slight deviations in our curves is likely due to not taking enough measurements near the beam waist.
To determine the waist size and Rayleigh range of the beam, we used the classical profiling algorithm. To start, we determined the waist size at each knife edge location, which can be found analytically by taking the difference between micrometer readings when the power measurement was at 84% and 16% of its max value in our plots. Then, we can use those waist sizes at each location and the distance between the locations in our calculations for beam waist size and Rayleigh range. When the knife edge was at the far location, we found that the beam waist was approximately 2 millimeters. Then, when the knife edge was at the close location, we found the beam waist was 0.834 millimeters.
After locating 16% and 84% of the normalized beam's intensity, we can calculate what the beam waist at position 1 and 2 are for when the knife edge is close or far away from the beam. The knife edge position being delta z. Using these values, we can use the quadratic equation relating these parameters to the Rayleigh range z naught. This gives us 2 potential solutions. Using these solutions, we can back calculate which one gives us the correct delta z value by solving for z2 and z1 for when these values are located on the same side of the beam waist using the z0 solution. The z0 that gives the correct delta z value is the correct Rayleigh range that we should use to calculate the beam waist. The zeros that were found were 14.34 millimeters and 51.5 millimeters. When we check these z0 values, we find that 14.34 fails, while for 51.5, this value passes, giving the right delta z value in the experiment. Therefore, the Rayleigh range is 51.5 millimeters, and the beam waist is 0.102 millimeters. Due to approximating the waist positions when at 84% and 16%, the calculated waist value is 1/3 the actual beam waist size.
Next, we took the beam profile after focusing the beam using a lens. We placed the 200mm focal length lens about 400mm away from the laser aperture and focused the microscope on the back surface. Using the same alignment technique as Lab 1, we centered the laser in the lens and adjusted the tip and tilt. We then performed the same procedure as before, taking a profile close to and far from the lens to get profiles on either side of the new beam waist after focusing.
Doing the same procedure as before for when there was no lens and moving the knife edge, including the lens, the only change is that we will now check the Rayleigh range value given from the quadratic equation using the correct z1 equation where both are located on opposite sides of the beam waist. This resulted in the zeros found being 71.62 millimeters and 168.72 millimeters. When checking the 71.62, we see that it passes and it gives us the correct delta z value, while checking for z0 equals 168.72 millimeters, it fails. Therefore, the correct Rayleigh range is 71.62 and the beam waist is 0.12 millimeters. Again, due to approximations, for the waist positions of 84% and 16%, our calculated waist value is 1/3 the actual beam waist size.
In this lab, we refreshed our understanding of Gaussian beams and how they propagate, as well as how to carry out proper alignment techniques. We learned how to profile a beam using a knife edge and use the classical beam profiling algorithm to determine important characteristics of a Gaussian beam.